I thought I'd go through part D, that ending part of section 2. This is the one where we get into some funky ones. It's kind of the potpourri of section 2. Really what this delves into is some AP problems and some typical AP problems you'll encounter. So they're going to seem probably a little bit hard at times, but we'll power through. So you are familiar with the general derivative definition using the limit explanation of calculating a derivative. And then there are two other ones that are called like alternate derivative definitions. These ones are more specific. They are located at a point. So my point being some value where c is equal to some number. I'm evaluating the derivative at a number. Okay, and you'll notice the format of that looks a little bit different. I no longer have the general x where I replace it with an actual value of c. But still, this notion of h going to 0 is still in play. In this case, it says x is going to c, so x minus c, if x is going to c, then I get 0 equals 0, or c minus c is getting close to 0. So all of them have that characteristic where the denominator is going to 0. What I want us to be able to do is to recognize these patterns of limit functions that really mean take a derivative or find the derivative. For example, this one says evaluate each of the following by recognition of the function as a limit function that defines a derivative. So the first thing that captures my eye is this delta x going to 0, and I have delta x on the bottom. Well, that means that I'm driving towards 0 here in the denominator, which is a problem, right? It's hard to divide by 0. This is a very similar problem had these all been h's, like we had learned, so that it becomes this general derivative definition of a derivative. So delta x or h, it doesn't really matter, just variables used, right, that are different. Some textbooks write it using delta x. Our textbook chooses to write it using h. Now, what I want you to notice is that all of this really is f of x plus delta x, and then I get the minus, and this portion here is f of x. Wow, look at this. These are those two components. So this limit, which looks tremendously scary, like if I'm supposed to calculate that limit, becomes super easy when you realize all this is asking is what is the derivative of your function. So be a little detective and let's try to figure out what the original function was. What did we plug x plus delta x into? Well, all of this would have been, you know, just big x's that x plus delta x replaced. So I would think my function was x cubed minus 5x squared plus 4x, oops, x minus 7. Also, we see it right here, don't we? That's the original function. So you're telling me this limit is finding a derivative? Yep, that's what I'm telling you. Well, then just find the derivative. We can use our shortcuts to do that. How awesome is that? This is the answer to this huge limit problem that looks scary as ever. That limit will boil down to the derivative. All right, the next one, B. Now I see 9 plus h. That could have been an x. I could replace those numbers maybe with x. This one I'm a little bit concerned with. But when I do a comparison, this reminds me, once again, I still have h going to 0. Screams that it wants a derivative, that this is going to calculate a derivative. So I compare it with what I have on top. I'm going to clear the screen. This seems to be a lot like that alternate definition of a derivative that evaluates at a point, the point being at x equals c. What would be my c value? Well, I think this here is my c value, don't you? Because I'd have c plus h. Oh, that must mean c is 9. This over here was f of c. And what's happening, this was at c plus h. So here's that limit definition, alternative definition all over h, and we have the h there. Okay, let's figure out the original function. Well, the original function, if I look right here, that would have been c plus h. Oh, the original function had to have been square root of x, which I could write as x to the 1/2. That makes sense then, because f evaluated at a c of 9 would be square root of 9 equals 3. Oh, I get it. They were just doing the reduced form of f of c, weren't they? They plugged in 9 to the square root and came up with 3. So sometimes this is a really tough place to look. You can't get much information from there. The better place to look is in the beginning where you have c plus h. You'll be able to uncover the function much easier. So just kind of bank that away in your memory. Now, the real question was, what is f prime of 9? But I'm going to have to just get the general derivative first. I'm going to use this version of my original function to use the power rule in order to get the derivative. And of course, that's going to be 1/2 comes down. I get 1/2 x to the negative 1/2, so that's a square root dropping to the bottom. And now, finally, let's just pop in the 9 and evaluate our derivative at 9. That makes this 1/6, doesn't it? Okay, the last one, once again, I hope that you see what I see. This h business, h is going to 0. Man, oh man, does this sound like a derivative problem, right? All we have to do is uncover what the original function was. Okay, here's my c plus h again. Oh, my original function then would have started out with a sine of x. And remember, this here is f evaluated at some c, so this has already been simplified. This is the simplified version of that calculation f at c. What is c? Well, I figured out c was pi over 3. Good. Now let's go into our derivative. Let's get the general derivative. That would be a cosine. Derivative of sine leads me to cosine. And last step, do the evaluation at a point at pi over 3. Okay, I can do that. Cosine of pi over 3 is 1/2. 1/2 is the answer to that problem. So there's one type of AP problem that's very common to see. This one is another one that perhaps would be more likely to show up on a free response. Given the function f of x equals x cubed plus kx, and a line y equals 6x minus 2, find the values of k such that the line is tangent to the function. So this is the function, this is the line they're referring to. And they want this line to be tangent to the function. Oh, this is a tangent line then. Got it. And this is our function. You know what? I'm just going to draw a basic cubic function. Basic cubic functions, that's not very good, is it? Try again. Maybe a little better. I have no idea where this is located because we got this variable that we're trying to uncover, this constant k that I'm trying to solve for. But what I do know is that there's a tangent line that's hitting my cubic function. Do I know exactly where it hits? No, but I do know that they have a point of tangency in common, or a point in common called the point of tangency. How is that helpful? Well, it gives me two things, you guys. One thing is that the equations have a point in common. They let's see, f of x and the tangent line share a point. Oh, it's like they intersect at a point? Yes, it is. Share a point. Which allows us to set the equations equal because they share a point. Equations equal. Okay, well, I could do that. X cubed plus kx equals my other side, 6x minus 2. Yeah, they share a point, so then the x value is going to be in common to them both. Let's just kind of pause at this one. Hang on to this thought. Now, I have two unknowns, so I need two equations. Let's create another equation. What else do I know about this situation? Well, I know this green is a tangent line. And the equation was y equals 6x minus 2. I'd draw this picture in your notes, you guys. Okay, from that, I can glean the information that, okay, this slope is 6. And I know that slope of a tangent line can be calculated by f prime of x has to turn out equaling 6, right? So we're going to work off the information about the tangent line. And the fact that the derivative of the function would have to equal the slope of the tangent line. Does that make sense? Alrighty, so I want to go f prime of x equals my slope of 6. Capture f prime of x. I'm going back, I'm looking. You can't see my eyes, but I'm looking upwards, you guys. 3x squared plus k equals 6. How did I get the k? Well, the exponent value of x is 1. So 1 comes down, multiplies by my constant, which is k, leaves me k, and then x to the 0. So now I have another fantastic equation. And if I have two equations with two unknowns, I can solve them together using a system. Use a system of equations to solve this. The method I'm going to choose to use is the substitution method. Why? Oh, because it's going to be easy. I'm going to take 3x squared plus k equals 6 and solve it for k. I told you that would be easy. Now we're going to use k and substitute k, k right here with our 6 minus 3x. So it's going to sub into x cubed plus kx equals 6x minus 2. So this will look like x cubed plus, instead of k, we're writing down 6 minus 3x squared. That was my k. I lost my spot, guys. X equals 6x minus 2. Notice we're down to all x's. That should be something that allows us to solve for x then. So I get 6x minus 3x cubed equals 6x minus 2. And negative 2x cubed. Subtract 6x from each side, that zeroes them out. That equals negative 2. Divide by negative 2, x cubed is 1. That makes x the cube root of 1. So x is 1. Helpful, but not the answer to the original problem. Look back to the original problem. It said find the k, find the value of k. So we need the value of k. Oh, well, remember how in systems of equations, sub it back over and we will get our k. K equals 6 minus 3 times 1 squared. K equals 3. An interesting problem. All based on the fact that we had a picture. The picture, I thought, unlocked this problem. They share a point, and we know the slope of our derivative. The slope of the derivative, it said that wrong. The derivative is equal to the slope, which is 6. This problem here asks you to determine whether it's continuous or non-continuous, and then it asks about differentiability. So we're going to do two steps. One, we're going to check for continuity first. How do I check for continuity? I use limits. I'm going to check the limit from the left. I'm going to start with the left because that's what's showing on my first piecewise. And I'm going to set that equal to the limit from the right. Oh, sorry. Oh, I said left, wrote plus, didn't I? In this one, since it's greater, will be from the right side. Alrighty, so, and then we're evaluating at 2. So we'll have 5x minus 11 evaluated at x equals 2. That's an evaluation sign when I draw that straight line. And then I need x squared plus x minus 7. Also evaluate that guy at 2. So that gives me 10 minus 11 on this side. On this side we have 4 plus 2 minus 7. Negative 1 equals negative 1. Sweet. Do you remember how limits are the definition of continuity? We talked about how it has kind of 3 parts to explore. We need to explore f of 2. Does it exist? Well, I know it exists because here was an equal branch. I've already explored this part. It looked like it came down to what, negative 1. And part C, do these parts equal? Does the value of the point, the y value, equal the limit as x approaches 2 of f of x? Yes, it does, and they actually all equaled negative 1, so I could throw that in there. That makes this function continuous at x equals 2. So that's the exploration on continuity. Sweet. Because it's continuous, it does have the possibility of being differentiable. Therefore, f of x is continuous. I just want to catch up on my notes here. Is continuous at x equals 2. The next thing we want to explore is differentiability. And I told you that in order to explore differentiability, or I need to, because if something is continuous, it has the potential then of being differentiable. Doesn't necessarily mean differentiable. Yeah, we're trying to discover, is this differentiable? So we had point number 1. Let's make this the second thing to explore. Is it differentiable? There is a theorem that says if it's differentiable, it's continuous. So I could reverse that logic and say if it's not continuous, then it's not differentiable. And then if this had turned out to be not continuous, I could say, well, immediately then it's not differentiable. But that wasn't the case for us, was it? Darn it. So because it is continuous, it has the potential of being differentiable. And let's see, what are we going to do? We are going to compare the limits of the derivatives. Remember that a derivative really comes from a limit definition. So I need to look from the left and the right of the derivative of each of these. So the limit as x approaches 2 from the right of f prime. Notice my prime symbols on this, right? We have prime and prime going here. I need to scroll back up so I can see my function and get that written in. So I want the derivative, which is 5 on this side. You know what I'm going to do? I'm going to give you one more step. D over dx, the derivative of 5x minus 11, just might be easier on your notes to understand what we did on this step. And then the derivative of the other branch, the right-hand branch of this piecewise. We want to explore these at x equals 2. So I'm just going to kind of make a note to myself. I'm going to evaluate these when x is 2. But first, let's do our derivative. I want to evaluate straight line. X equals 2 means evaluate this at 2. And then I'm going to go 2x plus 1, taking the derivative of this. And also will evaluate that at 2. Just, you know, it's hard to do so many steps at once. So this is just getting us through the process. And 2 goes in. 2 times 2 is 4 plus 1 is 5. Oh, so the derivative on the left equals the derivative on the right. It is f of x, rather than saying it, which is not very specific. F of x is differentiable, which means we can find the derivative at x equals 2. So in this case, our function has the characteristic of both. It's both differentiable and continuous. Now, if I wanted to, I could plot this line. I think I'll just plot points. At 2, I put in 2, and I'd have 5 times 2 minus that 11. Looks like it comes out to be negative 1. If I used, what number do I want to use? Let's use 1. 5 times 1 minus 11 gives me negative 6. So at 1, negative 6, about there. I end up with a line coming through there. It stops when x reaches 2. And our other one is a piecewise that is a parabola. And if I put in 2, I also get out -1. We checked that out on the limit side, didn't we? If I put in 3, I would have what? 9 plus 3 minus 7, 12. I would get a 5. So at 3, I get 5. Fairly steep. This will be climbing like in a parabola. And you know we got different shapes, or that shape for parabola. I doubt I'm picking up this portion of it, because then I would have a sharp change at 2. So sharp that it would not be differentiable. Remember, sharp corners are not differentiable. So I think the piece we must be picking up is more in line with this piece that's rising, and we get this nice smooth transition from this linear into this quadratic. So gradual that this slope was a nice matchup on that transition. All right. Finally, the last problem, find the values of a and b that make this function differentiable. All right, to be differentiable requires 2 things. One, it has to be continuous. So we would explore the continuous branch of the topic, and we'll also explore the differentiable branch. Can I take a derivative of it? So for continuous, it goes back to the idea of limit. I'm going to shortcut this a bit because I see we're already at 20 minutes. The limit from the left must equal the limit from the right at our handoff point, which is x equals 2. So plugging in 2, the left side would read 8a plus 1. The right side would read 2 minus 3. So I'd have b 2 minus 3 quantity squared plus 10. That's an 8a plus 1 equals -1 squared is +1, so a b plus 10. I think I will solve getting my variables on the left and my other work on the right. So subtract 1 gives me 9 on that side. Subtract b, I get that. All right, that's a good holding spot. Grab that equation. Don't lose track of it. For differentiability, here we want to check, the limit as we come into 2 from the left side of the derivative, and check to see that that equals the limit as we come into 2 from the right side of f prime. Now, f prime is not hard to take on the first one. It's going to be 3a squared, because a is some number. Really, in this scenario, it's a constant, isn't it? Plus 0, I need to evaluate this at x equals 2. The right side's a bit of a bugger because we don't have a great rule yet for this thing being squared. So to get around that, we're going to expand and do x minus 3 times x minus 3, which will give us x squared minus, that looks like a plus, minus 6 x plus 9 for that binomial expansion. Now let's send b through, and I'll have b x squared minus 6bx plus 9b plus 10. Notice that this would just be some number if I take 9 times a constant. I mention that because when we take the derivative, you're gonna have to think that through. So I take the derivative of the first stuff, and I get 2bx. The next stuff, the derivative of x would give us 1 come down, it would be a 6b. The derivative of 9b, since this is really just a number, that's going to be a 0, and the derivative of 10 will also be a 0, and I need to evaluate this at 2, since that's what my limit was. Okay, 2 goes in for x. This will stay at 3a squared, I guess. 2 goes in for x. I'm going to have 4b minus 6b. That's a negative 2b equals 3a squared. It looks right, doesn't it? So I get 3a squared plus 2b equals 0. Why did I think this was going to be 3a squared? That looks good. On the right side, we expanded x squared minus 6x plus 9, multiplied it by b, added 10. That gives me, for a derivative, 2bx minus 6b, 0, 0. Alrighty. Now I need to pull these two together. And that's going to be 8a minus b equals 9. Let's multiply this by 2. So 16a minus 2b equals 18. 3a squared plus 2b equals 0. And where does that take us? That gets me to 3a squared. Is that my problem? Oh my goodness, it is my problem. This just seemed wrong, you guys. I bet you figured out this, and I just figured it out too. When I took the derivative of this, I brought the 3a down and I said it was a squared, but it's not. It's x squared, isn't it? All right, now backtracking. 2 goes in, that gives me 4. I get 12a, and then I get 12a. And bringing everything together, I get 12a plus 2b equals 0. I'm loving this now. This is going to be so much nicer. I'm going to divide everything by 2, and that gives me 6a plus b equals 0. All right, now, much better system of equations here. Because we have negative b and positive b. So sorry. Bring these two together into a system, and voila, we get 2a equals 18. Oh no, how about a 14? 14a equals 18. Therefore, a equals 18 fourths, which is 9 sevenths. Cool. A equals 9 sevenths. B can be found very easily. I would just take it back over and solve out for B. And I'm going to not do that just because of time. That brings you to